Yesterday we were doing some questions on complex integrals, and I gave a homework that I'm going to start. I'm going to do today, and that would start your lecture today. So yesterday we were discussing complex integrals, and one of the questions that I gave you as a homework, I'm doing it right now. Okay. So the title would be complex integrals. Okay, or contour integrals, as you may wish to say. And we did one of the type of integral called as trigonometric integrals. Okay, so we did something called as trigonometric integrals. And what are trigonometric integrals? Integrals which are of the type, I think, where function is of some sine theta and cosine theta, and 0 to pi. What we do is we actually transform sine theta and cos theta, or change sine theta and cos theta in terms of e to the power iota theta, and we take e to the power iota theta as z, and all the procedure I have described in the previous class. Okay, so I left you with a question that was this way: integral 0 to 2 pi cos n theta d theta divided by 1 plus twice a cos theta plus a square. How to do this particular question? Let us see. Okay, so let us see how to do this particular question. Okay, so here it is. So yesterday I told you whenever such questions come, you have to just see, you have to just write all these things. Like I have written e to the power iota and theta and write real part, because real part of e to the power iota and theta would be equals to what? It will be equals to cos and theta divided by 1 plus twice a e to the power iota theta plus e to the power minus iota theta divided by 2. So this will get cancelled and only a would remain here plus a square. And if you place e to the power iota theta as z, then I told you yesterday itself that it will be derivative will be equals to iota e to the power iota theta will be equals to dz, and d theta can be replaced by dz upon iota z. Okay, is that clear? So this we can do. If we can do this, then this is real part of integral mod z equals to 1, and this will come out as z raised to power n divided by 1 plus, I think if you take it as z plus 1 upon z, then this will come as z square. 1 z would go here, 1 z would come here. So this will come as a. And here you will have z square plus 1 plus a square z. And divided by z would remain here. But then there would be something dz upon iota z. That z cancels this z. So overall, you are just remaining with, this kind of term. Okay. Now, further as we move, what would we do? We would be interested in finding what sort of singularities this particular function has. Okay, so this particular function I'm talking right now, this integrand. So I am interested in this integrand, and I want to find what sort of singularity does this have, because in order to find the integral, we should be able to figure out what is the nature of the singularity, because only then we will be in the position to find the residue. Okay, so the singularities would be at the place where your az square plus a square plus 1 z plus a. Okay, and this you just try to find the roots. Okay, and you'll find that there are two roots, that is z equals to minus a and z equals to minus 1 upon a. And hope I have given the condition. If I have not given the condition, that question cannot be solved. So kindly write a square should be less than 1. So if a square is less than 1, 1 upon a would be greater than 1. So if a square is less than 1, then 1 upon a would be greater than 1. If 1 upon a is greater than 1, then this particular singularity cannot lie inside the unit circle. Only this singularity will lie inside the unit circle. So let us first find this. Let us first find the residue about z equals to minus a. So z equal to minus a, singularity can be found, residue can be found out as limit z tends to minus a, z plus a into z ki power n. You just take a common out. Yesterday also I told you that only if you take a common out, only then you can factorize the quadratic equation in terms of its roots. Okay, so this gets cancelled. And overall, one can clearly see that only terms that remains is minus 1 raised to power n into a ki power n divided by a, and you will get 1 minus of a square upon a gets cancelled. So overall, this will be the answer. Okay, this will be the answer. Now, what is there? This will be not answer, sorry, this will be a residue. Now you can clearly see 1 upon iota. This entire thing will be equals to what? This entire thing will be equals to 2 pi iota multiplied by this. So what is the value of the integral? 2 pi iota into minus 1 raised power n, a raised power n divided by 1 minus of a square. And also one needs to see that you have to multiply with 1 upon iota also and take its entire real part. So iota gets cancelled with iota, and you are left with something which is only real. So real of real is, again, you have to just write this particular expression here. So what you'll get eventually, you'll get 2 pi minus 1 raised power n, a raised power n divided by 1 minus of a square. So yesterday, if I made this mistake of not giving you the condition that a square is less than 1, so kindly correct that question. But overall, you have to understand that only one singular, overall this is necessary because it will only be, only if this is given, then you can figure out what sort of singularities lie inside and what singularities lie outside the contour. Okay, so I hope this is it. Acha, okay, another question that I gave you in this particular thing only was sine and theta. Sine and theta divided by, I think it was the same question, 1 plus 2a cos theta plus a square integration from 0 से लेकर 2 pi d theta, given that a square is less than 1. So this will give you as imaginary part of z, imaginary part of integral 1 upon iota. You have z raised to power n divided by this entire thing. Okay, and you clearly know that this entire thing will come out as something 2 pi iota into something that I mentioned above only. So you can clearly see that this entire thing you have already evaluated. And when iota gets multiplied with iota, iota gets cancelled. So overall, this term will come out. And imaginary part to this term is 0. So clearly, this integral would come out as 0. So this is something that you can verify on your end, that the same steps you have to do, but only part is instead of real, you have to write imaginary. So if you write imaginary here, there is no such imaginary term inside. So overall, this integral will become 0. So it is fairly easy to see that integral 0 to 2 pi cos n theta d theta upon 1 plus 2a cos theta plus a square, this integration amounts to 2 pi a raised to power n into minus 1 raised to power n divided by 1 minus a square. And this integral, which is represented by integral 0 to 2 pi sine n theta upon 1 plus 2a cos theta plus a square d theta, where a square is less than 1, turns out to be 0. Okay, so let us move forward and let us see a few more integrals. Okay, so let us see a few more integrals. Okay, so now if you have integrals which are varying from, if you have some improper integrals, okay, so to speak, in more you can say in more rigorous way, if I say these are improper integrals. Okay, so I'll be doing today improper integrals, and these improper integrals we are going to do today by the help of complex integration. Okay, so we are actually coming to the end of the topic now. Hardly probably this week it would take and things will be done. Okay, so improper integrals, I would again make some certain types so that it becomes easy for you to follow. And initially I would take a few conditions. Okay, a few conditions I would take, and then we would see how to solve certain improper integrals using the complex functions. Okay, so if at all your function is in this fashion, minus infinity to infinity fx dx, and fx is a rational function, and fx is a rational function, then what we do, we replace this integral by a complex integral. So we replace this by a complex integral. Okay, and we take a contour which is of the semicircular shape. We'll see how things will work out here. The only condition is that the fz should be analytic. The condition is that fz should be analytic except for some finite number of poles. Except for some finite number of poles which lie on the upper half. Except for some finite number of poles which lie on the upper half of the plane. Okay, so upper half of this is semicircular plane only, so singularity is only lie on the upper half. Note that not on the contour itself. So not on contour. That is, it cannot be anywhere here or it cannot be anywhere on this entire semicircle too. So I'm giving it as gamma. So what we do, we replace this integral by this integral. And let's see how we further go. Also that we see that it should be the case that as mod z tends to infinity, or you can say that as r tends to infinity, if you take z is equal to some r e to the power iota theta, then your fz mod should also tend to 0. Okay, then fz mod should also tend to 0. If it is the case, and if it is the case, then only the step that I'm going to tell you will work. That is, I'm right now talking about functions which are generally rational functions. What are rational functions? Rational functions are nothing but it is equals to quotient of two polynomial functions such that hx should not be equal to 0. Okay, integrals of such type minus infinite to infinite fx dx, where fx is a rational function, can be evaluated using complex integrals. And what you can do is you can just replace this integral by this integral. Okay, and condition is that fz should be analytic except for some finite number of poles which lie on the upper half. So it is allowed that there can be singularities on the upper half. It has no problem, but not on the contour. What about contour? We'll see later on. The second condition is that if mod z tends to infinity or r tends to infinity, then your fz ka mod should tend to 0. I'll write all these conditions quite sophisticated lately. So overall, you have to understand this. Also understand there is nothing such uniqueness about upper half. You can take lower half as well. Okay, you can take lower half as well, and you will arrive at the very same answer. Okay, but only point is that when you apply this on the lower half, then your function should vanish. Your function should vanish on the lower half. Okay, so those cases we may take as we go along, but overall you understand I'm right now taking a case where I'm going to make a semicircular contour. Okay, semicircular contour, and I will see that integration over this entire gamma would come out as 0. Entire gamma means that not this entire closed curve. I would mean only this arc. So this will prove. Okay, this will prove today. Okay, so let us move ahead and do certain type of questions and first develop an understanding as to how we'll be moving ahead. Okay, so okay, also remember that such strategies can be applied for integral 0 to infinity also, fx dx, provided fx is an even function, provided fx is an even function. The same thing can be applied to even function also. You can write 1 by 2 and you can integrate from minus infinity to plus infinity, and whatever I'm going to tell to in this class, it can be applied to even functions with these limits 0 to infinity. Okay, I hope it is clear till now. Okay, so let us move ahead and
सर
हाँ जी बोलो.
ये क्या लिखा हुआ है आपने mod z tends to infinity और r tends to infinity f mod z tends to 0.
मतलब if your mod z tends to infinity, and see on this semicircular contour I can express z as r e to the power iota theta. So even if I say mod z tends to infinity or r tends to infinity, they mean one and the same thing. The condition is that as mod z tends to infinity or as r tends to infinity, your fz should vanish. Fz ka mod should tend towards 0. If this is the condition, and also that condition should be that fz should be analytic except for some finite number of poles, then whatever I'm going to do subsequently, will be a जनरलाइज्ड रिजल्ट. मतलब ऐसा समझो कि अगर ये दो कंडीशन ट्रू है तो जो मैं करने वाला हूँ यू विल फाइंड दैट यू कैन अप्लाई इट टू एनी प्रॉब्लम. आर यू गेटिंग माय पॉइंट? Well, these two are conditions. These two are conditions that I'm writing. भरत नहीं समझ में आया?
सर मॉड जेड जीरो मतलब
मॉड सेट जीरो नहीं
नहीं
बेटा.
समझ में।
अच्छा ओके. जैसे कि मान लेते हैं मैंने तुम्हें कहा, जैसे फॉर एग्जांपल आई विल गिव यू एग्जांपल, डोंट वरी अबाउट इट, यू जस्ट टेक द राइट. अभी एक बार को उसको ऐसे रहने दो एंड आई विल टेल यू,
ओके
उसके बाद समझ में आने लगेगा. ठीक है. देखो, सिंस इट इज अ रैशनल फंक्शन, since it is a rational function, I will write here. See, जैसे कि मान लेते हैं इंटीग्रल मैंने लिया. मैं एक बार एग्जांपल देता हूँ. जीरो से इन्फिनिटी, इसी एग्जांपल से आगे बढ़ेंगे. लेट्स से 1 प्लस एक्स स्क्वायर. कोई दिक्कत? आई टोल्ड यू दिस इंटीग्रल कैन बी क्या कह सकते हैं, रिप्लेस्ड बाय दिस सॉर्ट ऑफ इंटीग्रल. कोई दिक्कत है इसके अंदर? अब जो ये समझ में, ये तो मैंने यहाँ पे लिख ही दिया कि हम लोग जब इस
यस सर
प्रॉपर
है।
इंटीग्रल को इवैल्यूएट करेंगे, व्हाट विल डू, व्हाट इज द स्ट्रेटजी, विल this integral can be evaluated by using this sort of control. We'll see what how we'll do, but right now just I'm explaining this like last equation. So अब जैसे इसको इंटीग्रेट करोगे, so what you'll do, you have to see that your fz is what, your fz is 1 upon 1 plus z square, right? Instead of fx you're writing fz, and fz is integrated over this, so I can write z as r e की power iota theta, right? Now as mod z tends to infinity, it implies r tends to infinity, so mod z means mod r, sorry matlab,
यस सर।
okay. Now let us see, sorry, let us see ki what happens to this fz का mod. So I will see what happens to fz का mod. Let us take fz का mod. Fz का mod is 1 upon 1 plus z square मानते हैं. Okay. And this property I will write here. There's a property which suggests that z1 plus z2 will always be greater than equal to z1 mod minus z2 mod whole mod. This is triangles inequality. If you are not familiar, just write it down. Okay. So 1 plus z square का जो mod होगा वो किससे बड़ा होगा? It will be greater than 1 minus of z square का mod, ऐसा कुछ. 1 की जगह कौन है? z1, z
यस सर।
z2 की जगह. ठीक है. And you can take, I mean you can take a reciprocal of this and you'll find that this can be written as 1 plus z square का mod is less than equal to 1 upon 1 minus z square. Okay. And what is z square? Z square is nothing but it is equals to what? Okay. So you get, sorry, it is equal to mod z whole square, right? Mod z whole square. My mistake. Okay. So this will be equals to mod z whole square. Mod z क्या है बेटा? Mod z is r. So I can write it as 1 upon 1 minus r square का mod, right? Now as r tends to infinity, this entire thing will go towards zero, right? This entire thing will, इसका मतलब क्या हुआ? इसका मतलब ये हुआ कि I'm saying, इसका मतलब ये हुआ कि I'm saying that my fz का mod is less than equal to zero. किसी क्वांटिटी का मॉडुलस लेस देन जीरो तो हो नहीं सकता. होना क्या पड़ेगा? इक्वल टू जीरो. इट इम्प्लाइज fz का mod टेंड्स टुवर्ड्स जीरो as mod z टेंड्स टू इंफिनिटी. ठीक है. सो इस पर्टिकुलर फंक्शन की इवेल्युएशन में क्या क्या चीज आनी है? एक तो देख लिया हमने कि अगर मैं इसको रिप्लेस करता हूं तो एक तो हमने देख लिया कि fz का मॉड जो है वो टेंड्स टू जीरो जा रहा है एज मॉड z टेंड्स टू इंफिनिटी. सेकंड हमने देख लिया कि इसकी जो सिंगुलरिटीज आएंगी वो क्या आएंगी? प्लस माइनस आयोटा. माइनस आयोटा को भूल जाओ क्योंकि अपर हाफ में नहीं लाया करता, लेकिन प्लस आयोटा जो है वो अपर हाफ ऑफ द प्लेन में लाया करता है. कोई दिक्कत नहीं. ओके. अपर हाफ ऑफ द प्लेन में लाया करता है. सेकंड, और इसके अलावा क्या है? इसके अलावा क्या करना है हमको? हाँ बस ठीक है. एंड वी कैन इवेलुएट दिस इंटीग्रल यूजिंग दिस इंटीग्रल because it satisfies both these conditions which I stated. Are you getting my point?
यस
And so these are conditions. Like these are conditions after which is required for integration of this type to be evaluated using this sort of contour integration. Okay, so let us move ahead and see. So in general, you can see that these functions, since because you can understand that I'm talking about rational functions, so this will be some numerator divided by denominator. Numerator will also have a polynomial. Denominator will also have a polynomial. Okay. And obviously there would be some degree difference. Like numerator may have x square, then it will have x ki power 4. In any case, the degree of denominator should be at least greater than at least one or one greater than degree one no, sorry, two greater than degree of the numerator. Because see, when you place when you take this particular integral and you write this way, now z is some r e ki power iota theta, so dz will be r e ki power iota theta iota d theta. Okay, and fz will also have some r, and there will be some denominator. So this entire thing will vanish only if the denominator's degree is greater than twice greater than the numerator's degree. Okay, or you can say that after a certain reduction, your r term should only remain in the denominator term. Because if r remains in the denominator, only then, as r tends to infinity, the fz would tends towards 0. Are you getting my point? ये चीज समझ में आई?
Yes, sir.
So I would write this entire condition in a certain different fashion. That is, if it happens, that your fz ka mod can be written less than equal to m divided by r ki power k, where k is greater than 1. Then as r tends to infinity, this tends to 0, and fz ka mod tends to 0. So this entire condition that I'm writing in the second condition that I'm writing, I can reduce it to this. Okay, is that clear?
Yes,
Okay.
sir.
So देखो अब अपन चलते हैं इंटीग्रेशन पे. तो देखो what was our integration? Our integration was minus infinite to infinite fx dx, and the condition is this. Understand, this condition is there. Another condition I have written already above, that fz should be analytic except for some finite number of points, except for some finite number of poles that lie on the upper half. So what I would do is, so let's say anybody may say that आपका यहाँ iota है, you can make a semicircle which is small, but then it will not enclose the singularity. So what we give that condition ki we may take semicircular contour as large as we may wish, so that any finite singularity should come inside. Okay, this is the condition. Okay, so what I would do is, instead of evaluating this integral, I'm interested in this integral that I'm writing right now. This integral would be integration fz dz anti-clockwise, and you can say over this closed contour gamma. So what it will be like, so here it is minus r to r. Okay, so I will write minus r to plus r fz dz, no issues about it. Okay, plus integration over this, you can say, I'm writing semicircular arc. This gamma does not represent your closed contour. Here I'm writing gamma semi arc, means I'm talking about only this semicircular arc. Are you getting my point? So I'm writing fz.
Yes, sir.
Is that clear? Now this particular on the closed contour can be written as this. Now in order to see कि इसकी value क्या होगी, I have to take r tends to infinity. This is what I was telling. I can take the upper half semicircle as large as possible. Okay. Now as r tends to infinity, this will become minus infinity to infinity fz dz. Are you getting my point? And since I'm on the x-axis, whether I write z or whether I write x, one and the same thing, because on the x-axis, your y will become 0. And if your y would become 0, your z is what? Z is nothing but it is equals to what? Z is nothing but it is equal to what? It is equals to x plus iota y, right? And if your y is 0, then z is nothing but x. So you can write fz dz, or you can also write minus infinity infinity fx dx. Is that clear? So let us
Yes.
first evaluate what will be the value of this particular integral in the condition r tends to infinity. Okay, so as r tends to infinity, this will become this. Is that clear? But only point we want to know that this integral will go where. Okay, so we want to evaluate this particular integral goes where. So let us evaluate. So what I'm going to do is, see, I'm going to find the absolute value of this integral. Let us find the absolute value of this integral. So what I would do is I will simply take a mod. And I taught you on the very first day that this is a property, just remember it. Fz ka mod and dz ka mod. Okay. Understand my point. On this gamma curve, on this gamma on this gamma semicircular arc, dz mod represents what? Dz is small, infinitesimal small length. And infinitesimal small length when added would give you this length of the arc. Okay. And you already know that your fz ka mod is less than equal to m upon r ki power k, where k is greater than 1. Okay, so this entire thing would eventually be less than equal to m upon r ki power k, and this mod z will give you pi into r. Is that clear? If you can remember this, something of this sort I already did in something called as ML inequality. Is that clear?
Yes, sir.
So this pi is pi ki jagah rahega, r gets cancelled, so you are remaining pi m upon r ki power k minus 1, and k is greater than 1, so obviously k minus 1 would be greater than 0, so there is some residual term in the denominator which depends only on r. Now let us see as r tends to infinity how things work. So as r tends to infinity, this entire thing that I'm writing, integral mod fz dz, is less than equal to 0, because as r tends to infinity, this will become 0. Any modulus quantity cannot be less than 0. It implies what? It implies integral fz dz becomes 0. So this is what I was telling, that if you want to evaluate this integral, it is same as evaluating this integral, because as r tends to infinity, this will go 0. So you are left with this, and r tends to infinity means minus infinity to infinity fz dz. On x-axis, whether you write z or x, it is like minus infinity to infinity fx dx. Minus infinity to infinity fx dx becomes nothing, but it is equals to integral fz dz over closed contour gamma, where gamma is nothing. Gamma is a closed contour, is a semicircular closed contour on the upper half of the semicircle. Is that clear?
Yes, sir.
Okay. So most often you will see in TFR or in a net examination or in any sort of examination also. Otherwise, also you'll find that certain questions are asked on this concept only. Okay. So we'll do a few questions and then we'll move ahead. Okay. So a few questions. The question is, let us do an integral 0 to infinite dx upon 1 plus x raised power 6. So we'll do this question, that is 1 plus x raised power 6. What will be the value of this integral? Okay, you can clearly see that this integration cannot be done from your standard 12 things, because standard 12 thing would require something like 5x ki power 5, 6x ki power 5 here, because in order to have a substitution, in order to do a substitution, in order to perform a substitution, you need something associated with attached with dx, and which indeed is not the case here. Okay. So what I told you, I would replace this integral. Okay, one thing that needs to be done is I will write it as 1 upon 2 minus infinite to infinite, and I will write it as dx upon 1 plus x ki power 6. So I'll be evaluating this integral, and whatever integral comes, I'll multiply it with 1 over 2. So what I've told you, I told you that you have to integrate it over this thing. And already I told you that this will become equals to this minus r to r and plus some integration over semicircular arc. Just for your convenience, I'm again trying to convince you that this integration will be 0. Let us see how. I'm just trying to convince you. Eventually you have to accept this and you just need to do this integration. Okay. But right now, again, I'm convincing you so that if I find this integral over the semicircular arc, that is r e ki power iota theta, where theta lies from 0 to pi, I have to evaluate this thing. So this will be less than equal to 6. 1 plus z ki power 6 mod, and then here you have pi into r. And I already told you that 1 plus z ki power 6 mod is always greater than equals to 1 minus z ka mod ki power 6 mod. That is, it is always greater than 1 minus r ki power 6, and here it is 1 plus z ki power 6. Is that clear? And I can write 1 plus z ki power 6 ka jo mod hai, it is less than equal to 1 upon 1 minus r ki power 6. And this pi into r, even if I multiply, I'll get pi into r upon 1 minus r ki power 6 ka mod. And this is r raised to power 6. As r tends to infinity, this will go towards 0. So this integral will not contribute. So this integral will not contribute. Okay. So eventually I'm left with this integral only. And this integral would be equals to this integral. That is the integration of the complex function on the upper half of the closed semicircular contour. Okay, this is what I am left with. Okay, so let us find this integration. So let us find this kind of integration. So integration will be equals to dz upon 1 plus z raised to power 6 gamma. Let us first find what sort of singularities are here. So singularities will be z ki power 6 plus 1 equals to 0, and you will get z ki power 6 is equal to minus 1, and you will get z is equal to, I think, e ki power iota pi, or you can take, I think, 2n plus 1 iota pi divided by 6. Is that clear? Now you take n equal to 0, you'll get e ki power iota pi upon 6. You take n equals to 1, you will get iota, I think, pi upon 2. Or you can simply write iota, I think, 5 pi by 6. Then you'll get e ki power iota 7 pi by 6. Then you'll get e ki power iota 9 pi by 6, and then you will get e ki power iota 11 pi by 6, and then all the terms will come the same after one complete rotation. So you'll get, these are the 6 singularities that you're going to encounter. Is that clear? And all these singularities, I will write z1, z2, z3, z4, z5, z6. Basically what happens is I can write 1 plus z ki power 6 is equal to what? Z minus z1 into z minus z2 dash 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 z minus z6. So it is fairly easy to see that all these singularities, that is z1, z2, z3, z4, z5, and z6, are nothing but they are simple poles. They are nothing but simple poles. Also understand the fact that what all singularities would lie in this upper half of the semicircle. So clearly this singularity is not there, this singularity is not there, and this singularity is also not there. So you remain with only these singularities. Are you getting my point? Because this will lie on the upper half of the semicircle. You can see from the argument itself. Is that clear? Okay. So let us first find the residue about these points. Okay. So let us first find the residue about these points. So what will be the residue of fz about e ki power iota pi by 6? Let us first find that. So you are given this equation 1 upon z ki power 6 plus 1. So one way will be multiply it with, I think I will write it as z1, and take a limit z tends to z1, and you write this as, I think, z minus z1, and you write it as 1 upon z minus z1 and z minus z2 and all those things as just z minus z6. This gets cancelled, and you will write z1 z6 minus z1, sorry, this gets cancelled, and you're left with z1 minus z2 into z1 minus z3 into z1 minus z4, so on and so forth. But this will be very difficult for you. Instead, I told you on the very last day of our class that if your function can be represented by two analytic functions, a quotient of two analytic functions, what you do, you simply keep this alive, and clearly this is not 0. You just differentiate it. So residue would be equals to 1 upon 6 z ki power 5, whether you take this, whether you take this, or whether you take this. Are you getting my point till now? Yes or no?
Yes.
Okay. So what I would do is I would sum them up. So what is the sum of all residues? Sum of residue will be what? So I'm writing sum of residues, and sum of residues will be equals to 1 upon 6 z 1 upon z की power 5 तो पहले वाली रखो 1 upon iota 5 pi by 6 if I'm not wrong. The next is 1 upon e की power iota 5 pi by 2, and then 1 upon iota 25 pi upon 6. Is that clear? I don't think there is an issue till now. Okay. Okay, so now you just find these values, e ki power minus iota 5 pi by 6 then you find the value of e की power minus iota 5 pi by 12, and then you find the value of e की power minus iota 25 pi by 6. Okay, so let us do that. So what is 5 pi by 6? 5 pi by 6 is around 150 degrees. Okay, so what it will give you, this thing, just I'll find it here. So cos 5 pi by 6 plus iota sine 5 pi by 6. Okay, and this thing will come out as okay, so I'll do it anyway. So 5 pi by 6 is what? 5 pi by 6 is 3150. So this will be negative. So it will be cos pi minus pi by 6 plus iota. अच्छा एक नेगेटिव भी है तो दिस विल बी नेगेटिव हियर, है ना, और cos में नेगेटिव पॉजिटिव डज नॉट मैटर. ओके, सो cos इज माइनस cos pi by 6 minus iota sin 5 pi by 6. So or you can write minus, you can write it as, okay, so you are having this, I think, negative here, so here it will be some negative, and you can write pi minus pi by 6, so this will be pi by 6. I think I'm not wrong till now. भरत कोई गलती तो नहीं हो रही, देख लो प्लीज एक बार. So I don't think there is an issue till now.
Right.
Okay, so eventually you'll find that this particular thing is cos 30 degrees. Cos 30 degrees is, I think, minus root 3 by 2, and this is minus iota upon 2. Okay, so this is minus root 3 by 2 minus iota upon 2. Then plus, this is 5 pi by 2. So this is pi by 2. This is 3 pi by 2. This is again 5 pi by 2. And minus 5 pi by 2 is this. So basically, you're left with minus iota here, because sine will become minus 1. Okay. And then plus this entire thing will become what? So this entire thing I can write as e की power minus iota. This is 4 pi plus pi by 6, if I'm not wrong. And 4 pi plus theta. 4 pi plus theta, for cos and sine are both positive, so I will write it as e की power minus iota pi by 6. They mean one and the same, because after 4 pi plus theta, you're going to enter in the first quadrant. Whether you write cos or whether you write sine, they will become the same. That is, cos 4 pi plus theta is also cos theta. Sine 4 pi plus theta is also sine theta. So I think this will give you cos pi by 6 plus iota sine pi by 6. And you are left with root over 3 upon 2. And plus this time, this will be equals to iota upon. Okay, there's some mistake or what? Okay, let us see.
So
This
minus
gets,
है.
okay, minus and minus and minus. Okay, so this will become minus. कोई तो mistake हो रही है, ठीक है? तो this will get cancelled, and you are left with minus iota by 2 minus iota by 2. So you have minus 2 iota. So this is minus iota upon 3 from here. So sum of all residues is minus iota by 3. And further, you have to multiply with 2 pi also. No? So this will be 2 pi into minus iota upon 3. So you'll get, I think, answer as 2 pi by 3. And further, if you want to find the integration that it gave you, so that would be again 1 by 2, because this is integral from minus infinity to infinity. So you have to keep this care in exam. You don't have to make such kind of mistakes. So this is 2 pi by 3. So this integration would come out as pi upon 3. Is that clear? Because this integration came out as 2 pi by 3. Okay, is that clear to you?
Yes, sir.
Okay, you just try to find one more integration. That is, I think, given in the that came in the TFR examination only, if I'm not wrong. And you just try to find that integration. Overall, this is the kind of approach that you have to follow in these integrals that I've stated right now. Okay, just let me see and give you a question. Okay, and you'll find that these questions are asked almost every year. You'll find them every year in some exam or other, So you should prepare them well. Okay. So like this question, minus infinite to infinite, dx upon 1 plus x की power 4. Okay, so this was asked in CSIR NET June exam.
It was there in TIFR also, sir.
This was also in TFR. So you will find that such questions would always come. So in TFR, a sort of this question came. So you just try to, these two things I'm leaving you as a homework. You just try to solve them. If you want an answer to them, I'll give answer to them also. So 50, so you'll have this answer to this, pi upon 8, if I'm not wrong. Okay, and the answer to this is, I think the answer is, okay, it's called pi upon root. Try to find these two integrals, okay? So this is like, these kind of integrals are usually asked in the examination. Okay, now as we move ahead, if a certain different thing is done, like for example, if instead of this you are asked an integral of form like this that I'm going to write, where you have multiplied this entire thing with some exponential term. Like for example, I want to say that, for example, if my function fx that I was doing earlier had nothing such terms. But what if I have some term like e ki power iota mx, or if I not write e ki power iota mx, if I have certain terms like cos mx and sin mx, then how to go about these problems? So this is like third type of integral that we are going to do. Okay. Okay. So understand in these questions also. So I'll write here integration of type minus infinite to infinite fx, and you can have any multiplication, like you can have cos mx also, and you can have sin mx also. Okay, this integration again take the same contour, minus r to r, and this entire gamma. Okay, if and the conditions remains the same, that is your function fx should be a rational function which should vanish as mod z tends to infinity, and you have this term. Then you have to replace this integration by integration over closed contour gamma fz, and you just replace it by e ki power iota mz dz. Okay, and I'll explain you. Don't worry about it. How to go about these problems also, like I'll explain you. Okay, so
with the real or imaginary part in front of that.
हाँ बेटा हाँ yes नहीं it will take care of itself, don't worry about it. मतलब इसको तुम evaluate करने जाओगे, eventually you end up getting these terms, don't worry about it. So the condition is that your function obviously should vanish, that is z ka mod should be less than equal to m upon r ki power k as I took earlier, and fz should have some finite number of, should be analytic, or you can say except for some finite number of poles, you can say, or you can say that your function fz should be meromorphic on the upper half of the plane. And if you have this condition that f fz is meromorphic on the upper half of the plane, and second fz ka mod is less than equal to m upon r ki power k, then this sort of integration can be evaluated by converting into this. Let us see how. So as I told earlier also, this integration would be equals to what? This integration would be equals to, one integration that is from minus r to r, and another integration on semicircular arc. If I take r tends to infinity, this particular thing will be somehow I can write in this fashion. My concerns are for this integral. What about this integral? Okay, and it will turn out that this integral will also go towards 0. So let us see how. So if I try to find limit r tends to infinity fz e ki power iota mz ka mod dz on this semicircular arc. So this will be equals to what? On semicircular arc, I can write my z as r e ki power iota theta. Is that clear? So this will be equals to integration 0 to pi mod e ki power iota m, and instead of z you can write r e ki power iota theta, and in place of f you can write f of as a function of this thing, And instead of dz, you can write r e की power iota theta d theta. Is that clear? And eventually you will find that this integration, a mod, will be less than equal to 0 to 2 pi modulus of e की power iota m r e की power iota theta f r e की power iota theta, and you have this mod will become only one, this r, because e की power iota theta का mod is 1. This is it. Okay. And I will write, I'll solve it further and write this. एक काम करते इसको पहले पढ़ लेते हैं, ठीक है? I will solve it more. ठीक है? Okay. So this is like integration 0 to 2 0 to 2 pi, 0 to pi e की power iota m. You can write it as r cos theta plus iota r sin theta. This is one mod. Another mod is r f r e की power iota theta का mod, and then you have r d theta. Okay. So eventually you will find that here there is a term which is which remains with I. So anything which remains with I, that mod will become 1. So I'm not concerned there. I'm concerned with another term that happens to be e की power minus mr sin theta. Then you have this fz only, like r e की power iota theta क्या है? fz ही तो है. So you can write it as m upon r की power k. And it is less than equal to m upon r की power k, and you have r d theta. Is that clear? Now understand one thing. Sine जो होता है, it is a it is a function whose second derivative is negative. So such functions are called as concave functions. So concave function में क्या होता है? If you join arc, you'll find that it always lie below the curve. So like sin x कैसा फंक्शन है? sin x का डेरिवेटिव क्या होता है? cosine x, और cosine x का डेरिवेटिव क्या हो जाएगा? माइनस sin x. So 0 से लेकर पाई बाय 2 के बीच में फंक्शन का सेकंड डेरिवेटिव नेगेटिव आता है. Such functions are called as concave. Concave function में क्या होता है? You will find that your curve always lies above the chord joint. So let's say if I'm joining chord like this is pi by 2. So this is a point called as 0. This is a point pi by 2 comma 1 on the sine. This is point 0 comma 0. Try to write the equation of this line. This line will always lie below this curve. And this curve is what? This is sine theta. And when you find that this equation to this line, this is fairly simple to see that this line would be given by y is equal to, I think if I write theta here, 2 theta upon pi. It's fairly easy to see. You just take the 2-point form of the line and you'll find this kind of equation. So you can clearly see that your sine theta is less than equal to 2 theta upon pi. Okay. And why I'm doing so? Because this entire thing can be written as pi upon 2, because sine pi minus theta is sine theta only. So now from 0 to pi by 2, this I will write e की power minus mr sine theta. I can write it as, so I'll multiply with minus mr sine theta. Okay. So, I think we are about to close the class. So I would do this particular thing in the next class, so that because we are only left with 1 minute to go. Okay. So if you're not getting this point, I'll again come back to this point. Okay. So let us join in the next session.